All right, welcome back to the Deep Dives. As always, we appreciate you being here. You're here, and we're here because we all want to grasp those really crucial bits of knowledge without drowning in all the technical jargon, right? And
Yeah.
today we're going deep on something that's kind of hidden but really, really important in our modern electrical world, and that is K-factor rated transformers.
That's it. Yeah.
Now, you guys have the source material. It's a pretty in-depth technical paper on this topic. And our goal here, as always, is to break it down and really get to the core of what this K-factor rating actually means. But more importantly, why it matters so much for, a lot of the gadgets we use every single day depend on it.
Absolutely. And, we're talking about things that we take for granted, like computers, LED lights, all those fancy motor controls that help us save energy.
Boy, right.
They're great for efficiency, but they also bring some subtle but really crucial challenges to our electrical systems. And today, we're going to dive into one of those big challenges.
Okay, I like it. So the paper we're looking at jumps right in talking about these things called harmonic currents. And apparently these are produced by these things called nonlinear loads. Can you break those terms down for us? Like, what are they and why should our listeners care about them?
You got it. So imagine the electricity that powers everything around us, right? Picture it as this nice, smooth, consistent wave, okay? That's our 60 hertz fundamental frequency. It's the heartbeat of our electrical grid.
Okay, got it. 60 hertz.
Now, think of harmonic currents as like these extra little ripples or vibrations. They're kind of riding on top of that main 60 hertz wave. The thing is, they're not random. They happen at very specific multiples of that 60 hertz. So you get a second harmonic at 120 hertz, the third one at 180 hertz, and so on. It's a whole series of these like echoes of the main frequency. Now, both the voltage and the current can have these harmonics, but the paper is really focused on the current harmonics, and it says they're the ones that cause the real issues for transformers. So think of it like our nice, smooth electrical system is experiencing these little tremors, these little hiccups.
Okay, these tremors.
Yeah.
These specifically bother the transformers, huh? Why is that?
Yeah, that's the thing. These tremors, these harmonic currents, they generate extra heat inside the transformer. And it's not just heat. They can cause some mechanical stress, too. It's like shaking a delicate machine. Not good. Now, within this whole harmonic world, there's this one particular type of harmonic that's kind of a sneaky culprit, triplet harmonics.
Triplet. Okay, that sounds a bit ominous. What makes them different?
So, triplet harmonics are multiples of the third harmonic. That means you have the third, the ninth, the 15th, and so on. The tricky thing is that a lot of our everyday devices that are designed to be energy efficient are actually major sources of these triplet harmonics. Things like your computer's power supply, those energy-saving fluorescent lights, LED lights, they all contribute to this.
Huh? Interesting.
And now here's where it gets really, really important and why everyone listening should pay attention. You see, in a standard three-phase electrical system, which is what most buildings use, these triplet harmonics don't cancel each other out like some other harmonic frequencies do. Instead, they add up, and they add up specifically on the neutral wire.
Wait, so they add up, like they combine forces on that neutral wire. That's kind of counterintuitive.
It is, yeah. And the paper gives a really good example to illustrate this. Imagine you have just 1 amp of this third-order harmonic current on each of the three main power lines, the phases. What happens?
Yeah.
You end up with a whopping 3 amps of that 180 hertz current all flowing on that single neutral wire.
Wow, so it concentrates there.
Exactly. It's this hidden accumulation. Now, here's the contrast. Under normal conditions, with older, purely linear loads, think about old-school incandescent bulbs or simple resistive heaters, that neutral current is typically super low, almost zero.
Oh, okay. That makes sense.
So these added harmonic currents from all our modern gadgets, they lead to this significant buildup of heat. And it's not just in the neutral wires themselves, it's right at the transformer's connection points where the neutral comes in. That's where the real danger lies.
So even though each individual device might just be contributing a small bit of harmonic current, collectively, it creates this potentially huge problem. It's like death by 1,000 cuts, but electrical.
You got it. That's the core of the challenge we're dealing with here. And that brings us to the solution that the paper highlights. K-factor transformers. These aren't your everyday transformers. They're specifically designed to handle this whole harmonic overload issue.
Okay, so what's so special about these K-factor transformers? What's different about them that allows them to cope with all this extra harmonic current?
Well, one of the biggest things, and the paper really stresses this, is that they have a much larger neutral bar. It's beefed up compared to a standard transformer. In fact, there's this key safety standard, UL 1561, which mandates that K-factor transformers have a neutral bar that can handle roughly double, yes, double the transformer's full load ampacity.
Elbow. Wow, why is that extra capacity so important?
It all goes back to those triple unharmonics that left a gang up on the neutral wire. Remember that 75 kVA transformer example from the paper?
Yeah.
With a standard 208-volt AC secondary, it would normally have a full load current of about 360 amps. But a K-factor rated version of that same transformer needs a neutral bar that can handle a whopping 720 amps without breaking a sweat.
That's a huge difference.
It is. It's all about providing a much more robust pathway for that concentrated current to flow through. That way, the extra heat generated by those additive harmonics can be safely dissipated. Think of it like building a much wider escape route for all that concentrated electrical traffic.
Got it. It's not just about handling more current, it's about managing the extra heat that comes along with that harmonic current. Are there other internal modifications in K-factor transformers that help with this?
Oh yeah, absolutely. The paper talks about several other key design changes. Manufacturers might tweak the shape and arrangement, the geometry, if you will, of the actual wires that make up the transformer's coils. Sometimes they even use multiple conductors for each coil, kind of like braiding them together for extra strength. And then there's the core of the transformer itself. They might use higher grade silicon steel for that, and they might even add more air spaces between the windings.
So it's like giving it better ventilation and stronger internal components.
You got it. All these little tweaks, they all contribute to the transformer's ability to shed that extra heat generated by the harmonic currents. It's important to remember that these transformers don't eliminate the harmonics. They're built to withstand them, to keep going strong in the face of this hidden electrical stress.
Right, they're like the heavy-duty workhorses of the transformer world. So now let's talk about why these harmonics exist in the first place. The paper mentions this thing called notching in the current draw of certain devices. Can you explain what that means?
Okay, yeah. So imagine a device, let's say a variable speed motor drive. This is a common thing used to control the speed of motors in a lot of modern equipment.
Okay, right.
Now, to be super efficient, especially after it starts up, this motor drive doesn't just take a smooth, continuous flow of electricity. Instead, it kind of grabs power in these short, quick bursts, almost like little pulses. The paper uses the word notches to describe these dips in the current waveform. These quick grabs are all it needs to keep the motor running smoothly and efficiently, using less energy overall, and running cooler.
So it's like it's sipping power strategically instead of chugging it down.
That's a great way to put it. But here's the thing. These quick sips, while they're great for energy saving, they also create those harmonic currents. The paper gives the example of a 6-pulse variable speed drive, which is a very common type, and says that it primarily produces 5th and 7th harmonics, which are 300 hertz and 420 hertz, respectively.
Oh.
And these harmonic currents, they travel through the electrical system, generating heat in all sorts of components. And that brings us back to our K-factor transformers. They're designed to withstand that extra heat and keep everything running reliably.
Right, it's like a ripple effect. The quest for energy efficiency in our devices leads to these harmonic byproducts, and K-factor transformers are our way of managing those byproducts to prevent overheating and system failures. Now, the paper goes into some detail about the standards that govern these transformers and how that K-factor is actually calculated. It gets a bit technical with formulas and acronyms. Can you simplify that for us?
Absolutely. The good news is that there are very clear standards in place. Organizations like UL, which is Underwriters Laboratories, CSA, Canadian Standards Association, and IEE, the Institute of Electrical and Electronics Engineers, they all have specific standards that apply to both regular transformers and K-factor transformers.
Oh, okay.
These standards ensure that the transformers meet safety and performance requirements. The paper mentions UL 1461, CSA C22.2, number 4713, CSA C917, IEC 57.96 and IEC 57.110. These are like the rule books that manufacturers follow to make sure the equipment is safe and reliable for different electrical loads.
Right, the quality control manuals. And what about the K-factor calculation itself? That formula looked pretty intimidating.
It might look complex at first glance, but the basic idea is to quantify how much harmonic current a transformer can handle. The formula essentially looks at each of those noisy harmonic frequencies. Remember those multiples of 60 hertz and how much current is riding on each frequency relative to the main 60 hertz current. And importantly, it gives more weight to the higher frequency harmonics because they tend to cause more heating inside the transformer.
So it's a way to measure the level of harmonic stress a transformer might be under.
Exactly. And that number is the K factor. The paper mentions that this factor can range from 1 to 50. Now, what does that actually mean in the real world when you're picking a transformer? A K factor of 1 basically means the transformer is intended for those clean, smooth 60 hertz loads, the ideal scenario. But as that K factor number goes up, it indicates that the transformer is designed to handle more and more severe harmonic environments.
So higher K factor equals tougher transformer.
Exactly. A K factor of 50 is for the really extreme cases where you know exactly what kind of harmonics you're dealing with, like in very specific industrial applications. But more commonly, you'll see K factors of 4 or 13. These are the workhorses for handling moderate to significant levels of harmonic distortion that you find in a lot of modern buildings and industrial settings.
And how do I know if a transformer has a specific K factor? Is it like a label?
Yep. You got it. If a transformer is K-rated, that K-factor value will be clearly marked on its nameplate right there with all the other important information.
Okay, that makes sense.
Now, here's another important point. The K-factor isn't just some arbitrary number. It directly tells you how much bigger a standard non-K-rated transformer would need to be to handle the same amount of nonlinear load without overheating.
So it's a measure of how much extra capacity is built in to handle those harmonics.
Exactly. A higher K factor means you don't need to oversize the transformer as much, which can save you space and money.
That's practical.
Very much so. Now, the paper has this really handy table that gives general guidelines for K factor ratings based on the type of application. Let's walk through a few examples so our listeners can see how this applies in the real world.
Sounds good.
Okay, so a K1 rating is suitable for your basic, everyday applications with minimal harmonic generating loads. Think standard incandescent lighting, simple motors without variable speed controls, things like that. In these cases, the total harmonic distortion is usually less than 15%.
Right, the simpler stuff.
Exactly. Then you move up to a K4 rating. This is often used for things like induction heating equipment, SCR drives, and AC variable frequency drives. These systems are used to control motors precisely and efficiently, but they can generate a fair amount of harmonics. In these applications, you might have up to 50% of the connected load producing significant harmonics.
So K4 is for the more sophisticated motor control systems you see in a lot of modern buildings, right?
You got it. Then we step up to K13. This is common in places like schools and hospitals where they have a lot of electronically controlled lighting. These systems can produce a lot of harmonics, and in these environments, you could have anywhere from 50% to 100% of the connected loads contributing to harmonic distortion.
Wow, that's a lot of harmonics.
It is. And then you have K20. This is typically for data centers packed with computer servers and for critical care facilities and hospitals. These places have a ton of electronic equipment running constantly, generating a high percentage of harmonics, and the transformers are often under heavy load.
So K20 is for those mission-critical applications where reliability is absolutely paramount.
Absolutely. And finally, you have those K30 to K50 ratings. These are reserved for very specialized industrial applications where you have known, consistent, and often very intense harmonic generating loads.
So the higher you go on the K-factor scale, the more specialized and heavy-duty the application. It's fascinating to see how the increasing reliance on electronic devices has driven the need for these higher K-factor transformers. Now, the paper makes a couple of really important points that I want to highlight for our listeners. The first one is that the K-factor rating is a measure of a transformer's ability to survive the heat from harmonics, not to eliminate the harmonics themselves. Can you expand on that distinction?
Yeah, this is super important to understand. A K-factor transformer is built tough. It's designed to withstand the extra heat from those harmonic currents without getting too hot itself and failing prematurely. It's not about filtering out the harmonics, it's about enduring them.
So it's built to take the punishment.
Exactly. And to make it tougher, manufacturers use more core material, more windings, and special construction techniques that help dissipate heat better.
So if you install a K-rated transformer, you're not magically getting rid of harmonics, but you're ensuring that the transformer itself can handle.
Exactly. The harmonics are still there, but the transformer is much less likely to overheat and fail because of them. The other interesting point the paper brings up is about the efficiency data that manufacturers publish for these transformers.
Okay, what about it?
Well, because of energy efficiency regulations, manufacturers usually provide energy loss data for K-rated transformers based on how they perform under ideal conditions, with a perfect 60 Hz sine wave, no harmonics. This is done so they can be compared to other transformers in terms of energy efficiency.
I see. So the efficiency numbers you see in the specs might not reflect how the transformer performs in the real world with all those harmonic loads.
That's right. It's something to keep in mind. The paper also briefly mentions these things called harmonic mitigating transformers, or HMTs, and says they are different from K-factor transformers. What's the difference?
Okay, yeah, what's the deal with those?
So HMTs are a step up in terms of technology. Unlike K-factor transformers, which are designed to withstand the heat from harmonics, HMTs are actually designed to reduce the amount of harmonic current flowing in the system. They use more complex designs, often with multiple sets of windings and special core configurations that can cancel out certain harmonic frequencies.
So they actively fight the harmonics instead of just enduring them.
Exactly. They're more sophisticated, but they're also more complex to design and implement. The paper rightly says that HMTs deserve their own deep dive, and I think that's a great idea for a future episode.
Definitely something to explore. All right, let's wrap things up with a quick summary. We've learned that our energy-efficient electronic devices, while great in many ways, introduce these unwanted harmonic currents into our electrical systems. And those triplet harmonics are especially troublesome because they add up on the neutral wire, creating extra heat. To deal with this, we have K-factor transformers, which are specifically designed to withstand this additional heat. They have things like oversized neutral bars and other internal modifications that help them dissipate the heat. And that K-factor number you see on the transformer's nameplate tells you how resilient it is to those harmonic-induced heating effects.
That's a great summary. And as we become more and more reliant on these nonlinear electronic devices, understanding K-factor transformers becomes increasingly important for ensuring the reliability and safety of our electrical infrastructure.
Couldn't agree more. And this brings us to a final thought for you, our listener. Think about it. Our homes, our workplaces, they're filled with energy-efficient devices, but many of them produce these harmonics. So how do we adapt? How does our understanding and application of K-factor transformers need to evolve in the future of electrical system design? It's something to ponder. Maybe even take a look around your own environment and consider the impact of harmonics, and perhaps explore the differences between those tough K-factor transformers and those more advanced harmonic fighting mitigating transformers. Thanks for joining us for this deep dive. We'll see you next time. All right.